Okay, suppose we have an equation like 2x equals 10, and we're asked to solve for x. Before we go into the algebra, let's take a moment to figure out what this equation is saying in words. In words, all this is asking is, or all it's telling us is, 2 times something, and that something we're calling x. 2 times x equals 10. 2 times x equals 10. That's what this equation is telling us. Well, you might ask, well, how did you know this was 2 times x? Because I didn't see a multiplication symbol. Well, it's conventional, or it's usual in math to not include a multiplication symbol in a situation like this because it can get a little confusing. Let's see what I mean by that. If I were to write out a multiplication, a traditional multiplication symbol, I would write 2 with a multiplication symbol x equals 10. And you can see already that I have a little bit of uncertainty here. I've got 2 multiplying x, 2xx, 2. These two symbols look very similar, so we try to avoid writing 2 multiplied by x out like this with the traditional multiplication symbol. We might also see a little dot to represent a multiplication. Now, this involves less confusion, but still it's an extra symbol in between. But you might see it written like this on occasion. So all we mean by 2x is 2 times x equals 10. Okay, so how do we actually solve for x or find x? Well, one popular way in the beginning, when we're just starting out with some simple examples like this, my students like to think about it. They like to figure out what number times 2 gives me 10. So they'll go through different trial and error methods, and eventually you come up with 2 times 5. 2 times 5 equals 10. And so naturally you realize x is 5. So just thinking about it, let's put a little thought cloud above x. It's thinking about being 5. Little thought cloud there. Okay, so x is thinking about being 5. But let's go back a bit or think about this. If I had a more difficult equation, it might be hard to figure out what x is. So we need a more general approach, a little bit more systematic approach to help us figure out what x is all by itself. So in order to do that, we need to have a way of isolating x, or getting x all by itself on one side and everything else on the other side of the equation. So the way we can do this is we think, okay, 2 times x. If I want to undo or cancel out multiplying by 2, then what I want to do is divide by 2, so that we have 2 times x divided by 2. The 2's cancel out and leave us with x all by itself. But we can't do this just to one side of the equation. In order to keep the equation balanced, we've also got to divide by 2 on this side. So think of it as just whatever we do on one side of the equation, we need to do it on the other to keep it balanced. You'll hear this a lot with your teacher in an algebra class. What we do to one side of the equation, we must also do to the other. As long as we do it on both sides, you keep the equation balanced, we're okay. So here we've divided both sides by 2 because we want to cancel out multiplying by 2. Now, a nice result happens when we divide both sides by 2 on the left-hand side. We have x all by itself, and that's exactly what we wanted. On the right-hand side, the 10 and the 2 cancel out, and 10 divided by 2 is just 5. So we're left with x equals 5, and that agrees with what we thought x would be in the first place. So far, so good. Okay, now, what I'd like to do is visualize this. Let's get a visual. So now we're going to visualize the solution. All I mean by visualize is we want to draw a picture. Let's draw a picture to see what's happening. And for some people that helps to see this visually. So let's since we're going to think about this a little bit differently, I'll use a different color. Let's use green. Start off with the same equation, 2x equals 10. And so now visually, what does 2x mean? Well, it's just adding x plus x. By definition, if we have two x's, we can write it as a sum of x plus x. If I had 3x, I could write 3x as x plus x plus x. And that's just using the definition of multiplication. Now, on the right-hand side, I'm going to show this 10 visually as maybe 10 apples. You could say 10 peppermint candies or 10 chocolate bars, but I'm just going to use 10 apples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just want to have 10 separate objects on the right-hand side, and I've separated the two x's out into x plus x. Now, what we did up here was we divided the left side by 2. So what I'm going to do here on the left side is divide this into two groups. One group of x and another group of x. This is dividing this side into two equal groups. That's all we did before, is we divided by 2. Now I'm just dividing the left side into two equal groups. So now I'm going to divide the right side also into two equal groups. And what you see is that on the left side, each group has an x in it. And on the right side, each group has 5 apples. And so each of these x's represents 5 apples. And so let me go back to my green. So each x represents 5 apples. 1, 2, 3, 4, 5. And so what I've just shown you visually is that x equals 5. 5 apples, 5 people, 5 candy bars, whatever you like. So x is equal to 5 apples here. Now, before we finish and move on to the next example, one thing that teachers love for us to do is to check our work. So we want to finish this problem nicely by checking to see that x equals 5 actually works. And, of course, we've already done this in three different ways, so we're pretty confident that x will equal 5. But formally, the way we do this is we just go back to the original equation, 2x equals 10, and we want to substitute 5 wherever we see x. So let's just say 2 times, let's use a different color just to emphasize that we're plugging in this number, 2 times 5, you're probably already finished as I'm working my way through this, 2 times 5 equals 10. Well, yes, that's true. 2 times 5 does equal 10. We were wondering if that was true, and we plugged in 5 for x, and we realized 2 times 5 is equal to 10. And so x is 5. And we were right all along, which is exactly what we expected. Okay, so now let's try a similar example with a twist. Let's do a little line here to separate this to help us organize what we're doing. Okay, so now let's take a look at an example similar, but it requires one extra thought. Let's say we have 2. Oh, and by the way, we don't always need to use x's. We can use a different letter. So let's try a different letter in this case. 2a plus 3a equals 20. And we want to solve for a in this case. Well, this doesn't look exactly like what we started with before, where we have a number times the variable equals a number, but we're pretty close to that. If we have something like 2 apples and then we add 3 apples, we end up with 5 apples. So if we have 2 a's and then we add that to 3 a's, we will end up with 5 a's, or just 5a. And so 5a equals 20. Now we have an equation very much like what we had before with 2x equals 10. In this case, now it's 5a equals 20. And so I would imagine you're thinking, oh, I want to get a all by itself. I'm multiplying by 5. So in order to cancel that 5 out, I need to divide by 5. And then our number one rule in algebra, if we do something on one side of the equation, we must always do it on the other side as well. So we divided by 5 on the left side of the equation, so we want to divide by 5 on the right. So now these 5's on the left cancel out, and we're left with a all by itself. That's good news. And on the right, if we cancel 20 divided by 5 is equal to 4, and we end up with a equals 4. And if we want to do a quick check, because we always want to check our work, especially in the beginning, so if we do a check, we want to plug 4 in wherever a is. So let's try 2 times 4 plus 3 times 4. 2 times 4 plus 3 times 4. Is that equal to 20? Well, 2 times 4 is 8. And 3 times 4 is 12. And 8 plus 12 is 20. So that checks out, and we have a equals 4. Okay. So that gives us a quick summary on how to solve basic equations of the form a number times a variable equals a number. I hope this helps, and I look forward to seeing you in the next tutorial.